In this video, I want to introduce the CMOS NAND gate and the CMOS NOR gate. But let's first review some simple logic. Let's review AND logic and OR logic. At the left, I have a voltage V, and I have a switch that I'll call switch A, and I have a switch B. And I have a light bulb. And if this voltage V is attached to the light bulb, it'll light up. Over on the right side, I have an OR structure. Let's call this switch A and switch B. So AND logic means that I have to close this switch and this switch for the bulb to light up. Now, OR logic means that I can close this switch or this switch and have the bulb light up. So in this case, the AND required both switches to be closed for the event to happen. In the OR logic, it only required one switch to be closed for the event to happen. So in electronics, we have some symbols for the AND logic and the OR logic. The symbol for the AND logic is this, where this is, say, input A and input B and output. Now the OR logic symbol is slightly different. It has a curve as input. We call this input A in our example, input B, and it has an output. So we can think of this, we can think of say a light bulb at this output tied to ground. So if the A input is at a logic 1 and the B input is at a logic 1, then only in that situation will the output be a logic 1, and we'll apply a voltage and our light will shine. In the OR gate, let's also assume we have a light bulb attached to the output. Here's the filament tied to ground. Now in this case, if either input is at a 1, if this is at a 1, doesn't matter what A is doing. If B is at a 1, the output will be at a 1 and the light will shine. So in CMOS, we can generate the AND function and we can generate the OR function. But it's more simple to generate what we call the NAND function and the NOR function. It requires less transistors to generate those functions. So let's consider what a NAND function is. If we take this AND function with our input A and our input B, and we add an inverter to the output, we end up with what is called a NAND gate. Now to make a NOR gate, we do a similar thing with the OR symbol. We take the A input, B input. Now the output, again, we add an inverter. We invert the output signal, and this is called a NOR gate. Now this is a rather complex symbol, so in reality we can simplify this symbol, and we'll just put a bubble. Rather than drawing the entire inverter here, we'll just put a bubble. And now this becomes the conventional NAND gate symbol. This is input A input B, and output. So this means not AND. So NAND means not AND, and this is the NOT symbol. And this part is the AND gate. So in a similar way with the NOR gate, we can simplify this symbol. This is the A input, B input, and we'll show the inverter as just a bubble with an output. And this is called the NOR gate, meaning not OR. So this is the OR part, and this bubble is the NOT in the not OR. So if we, for example, have this A at a logic 1 and the B at a logic 1, the output of the AND gate will be at a logic 1, but the output of the NAND gate will be at a logic 0. So it requires both the A input and the B input being at a logic 1 to make the output a 0. Any other condition will cause the output to go to a 1. Now in the NOR gate, if we have a 0 at this input and a 0 at this input, we have a 0 at the output of the OR part, or a 1 at the output of the NOR. And if either the A input or the B input goes to a 1, the output will go to a 0. So let's see how we can construct the NAND gate and the NOR gate using the CMOS technology. Let's first construct a CMOS NAND gate. Let's say that we have a power supply, and let's set the power supply to 2 volts. And let's draw a p-channel transistor, and another p-channel transistor. Let's connect the p-channels in parallel and connect N channels in series to ground. Now let's label this input A, and this gate of the PFET will label input B. And let's connect input A to this NFET and the input B to this NFET. And let's label this our output. So this is the CMOS NAND gate. The unique condition occurs when both the NFETs are on. So if we have a logic 1 at A and a logic 1 at B, both NFETs are on and are resistive, and they pull the output down to ground. So the output becomes a 0. And if both inputs are 1, both PMOSs are turned off. Now let's construct the CMOS NOR gate. So again, let's say this is our power supply, and it can be 2 volts. We'll connect our PMOS transistors in series. And let's connect our NMOS or our N-channel transistors in parallel. So let's call this input A, input B. Let's connect input A to the gate of the NFET and input B to the gate of this other NFET. And let's label this our output node. The unique condition here is when both PFET transistors are in the on condition. So if this A input is at a 0 and the B input is at a 0, both the PMOS transistors form resistive elements. The output is connected as a logic 1. It's connected up to the power supply. Now that means that we have a 0 at this A input and a 0 at this B input, which means this NFET transistor is off and this is off. So that allows the output to go to the logic 1. Now any other condition on the input, for example, if this A signal is at a logic 1, this transistor is then on, and if A is at a logic 1, this PMOS is out of the picture, he's off, and our output is then at 0 volts, or logic 0. So let me label this as the CMOS NOR gate. So far in my example, I've shown 2 input NAND gates and NOR gates. So this shows how we can make a 4 input NAND gate. It's very simple. We just add more series transistors and more parallel transistors. If we want to make a 4 input NOR gate, we would add 4 series PFETs and 4 parallel NFETs. So it would be very similar. So let's consider what we can do with the NAND gate and the NOR gate. So here's a simple circuit using two input NAND gates. Now this is called a SET-RESET latch. And let me label this input not set and this input not reset. Now not set and not reset are normally at a logic 1 level. And I'll draw this as a logic 1. And not reset will normally be at a logic 1 level. And in that situation, these NAND gates act like inverters. So the top NAND gate acts like an inverter, the bottom NAND gate acts like an inverter, where this output connects to the input, and this output connects to the input of the other inverter. So this is just a memory element. You'll recall this from previous videos. If this is a 0, it's a 0 here, we produce a 1, and a 1 feeds back and it locks in the 0 here. So if both not set and not reset are at a logic 1, this behaves as a storage element. So let's see what happens if I bring the not set at some time to a 0 level. And when this goes to a 0, this will be 0, and this will be forced to a logic 1. Doesn't matter what the other input's doing. A 0 on a NAND gate always forces the output to a logic 1. And since the not reset is at a logic 1, this logic 1 becomes inverted, becomes a 0, and that 0 reinforces the logic 1 at the Q output. So when not set goes to 0, I set the Q to a logic 1. Now, let's say that I've set Q to a logic 1. I've dropped not set to a logic 0. Now at a later time, I want to drop not reset to a 0. So when this becomes a 0, this is a 0, that forces this to a 1, and a 1 here, and a 1 at the not reset forces to be a 0, and a 0 comes along and reinforces this 1. So the not reset sets the Q to a 0 level when it goes low. So this is a nice little circuit for storing information. So why don't I give you a homework problem, a simple homework problem. Why don't you make the SET-RESET latch, instead of using 2 input NAND gates, use 2 input NOR gates. So put the video on pause and see if you can figure that out. Then come back and I'll give you the solution. Okay, so I assume you've given it a shot, and let's do this SET-RESET latch using NOR gates. So let's make this a 2 input NOR gate, and like the NAND gate, let's draw another NOR gate down here. Let's connect this output to this input. Connect this output over to this other input. And let's change this to reset, and this we'll call set. And let's label this as Q and not Q. So this is very similar to the NAND case, except the reset and the set signals are normally at a logic 0 level. The set is at a logic 0 level. So when the reset goes to a logic 1, that forces this to a 0, and the set being a 0 forces this to a 1, and that 1 reinforces the 0. So the reset sets the Q to a logic 0. And in a similar way, when the set goes high, let's say at a different time here, set going to a 1 forces this to a 0. This being a 0 here and a 0 here forces this to a 1 that reinforces the 0. So the set signal sets the output Q at a logic 1. So it's very similar to the NAND gate case, except the input polarities are inverted on the set and the reset inputs.